Greetings. Welcome to Electronic Circuits 1. I am Behzad Razavi, and this is lecture number 30. Today we will begin to formulate the behavior of a MOS transistor and try to derive its IV characteristics. But before we go there, let's take a look at what we learned about MOS devices last time. So here's a simple diagram of what a MOS device looks like. We said that in a sense it's a capacitor. We have a conductive plate up here, which we call the gate, another conductive plate down here, which we call the substrate. Not a very good conductor, but a conductor nonetheless. And then some sort of insulator between them, which is in this case made of oxide. So if we place charge, for example, positive charge on the gate, then we would need negative charge over here. And then to that, we added two other terminals, one on this side, the source, one on this side, the drain. And our concept was that if we have some mobile negative charge around here, which we call the channel, then we can have current conduction between source and drain if we apply a voltage difference between these two, a battery between these two. So what we were thinking is perhaps we can generate a channel of electrons here, free electrons, by applying a positive voltage on the gate. Because if the gate voltage is positive enough, then we attract electrons to this interface and they serve as the channel. And more importantly, as this gate voltage becomes more positive, we have more negative charge here, meaning a higher density of electrons, which means, in a sense, the resistance between these two terminals goes down, and the channel becomes more conductive, and for a given voltage, we get more current. So we are thinking that maybe this will give us a voltage-dependent current source or something along those lines. That's the ultimate objective. All right, we also defined the concept of the threshold voltage. We said, as the gate voltage increases, while the source and drain are at 0, and the substrate is at 0, initially we only expose negative ions here, forming a depletion region, and we have no current. But at some point, at some particular gate source voltage, which we call the threshold voltage, we do begin to see electrons at this interface right here, free electrons, and that's when we begin to form a channel. So very qualitatively speaking, we said that if you try to plot the drain current, the current that flows here, as a function of this gate voltage, we would expect something like this. First, we have no current because we have only a depletion region as the gate voltage goes up. But then once the gate voltage reaches VTH, we begin to form a channel. Now we can have current conduction between source and drain, and we begin to see some current. All right. We also looked at the current that flows from source to drain or drain to source as a function of the drain voltage. So this time we have a certain gate voltage to exceed the threshold. So the device has some channel. We say the device is turned on. And now we play with the drain voltage. So the source is at 0, the drain voltage is going up. We would like to see what happens. Well, if we view this channel as a resistance, then as the voltage across the resistance increases, so does the current. So we should expect that the current increases with the voltage. Now, whether it's exactly linear or not, we don't know, but something along those lines. So today, we would like to formulate these characteristics and see what type of equation we can obtain so that we don't have to draw this device every time. We can just look at it as an abstract mathematical model that we can use in our circuit analysis and design. All right, so let's go ahead and look at what we want to cover today. To reach the derivation of IV characteristics, first we need to understand the behavior of the channel of electrons a little better. So we'll dig into that, and then we will begin to derive the IV characteristics. So how does the current flowing from drain to source vary as a function of the gate voltage or as a function of the drain voltage? Those are our objectives today. Very well. So Let's start by looking at the behavior of the channel. For now, just a qualitative understanding that we would like to develop. Okay, so we consider two cases. Case number one, the source is at 0, the drain is at 0, and we just have a positive gate voltage above a threshold, so we have some sort of channel. So let's do that. So case number one, VGS is greater than VTH to have a channel, and then VS and VD are equal to 0, and of course the substrate is also connected to 0. Okay, so that's easy. We just draw the MOS device again very quickly. Here are our source and drain, and we have some sort of voltage at the gate, which we call VG, going to 0. The source is at 0, the drain is at 0. Okay, and of course this is our oxide. So do we have a channel? Yes, because the gate voltage is greater than one threshold. All right, so we have some electrons here. Electrons here, 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 but there's no current. Why? Because this voltage and this voltage are equal. If the voltage difference across anything is 0, we can't have a current, right? So there's no current. Well, I shouldn't say anything, but at least across a resistor is 0. Okay, so then the situation is interesting because we have some charge carriers available, the electrons. We have electrons here, but there's no current because we haven't applied a voltage difference. So this is an interesting device because it is turned on, but it has no current. So I would like to mention that very explicitly so that you remember this in the future. Turned on, but has no current. That's a pretty strange device, isn't it? For diodes, when we turned them on, we had current. Right? They were at a given voltage, we had some current. But here, this turned on, but doesn't have voltage, doesn't have a current. Similarly, if you are familiar with bipolar devices, when a bipolar device is turned on, it must have a current. But here, we don't. Okay. So far, so good. If I ask you, find the density of electrons here, or here, or here, or here, you would say they all have the same density. That's obvious, right? Why is that? Well, we have a capacitor from here to here, and the charge that accumulates on the two plates of the capacitor is in proportion to the voltage that we have. So we know that Q is equal to CV. So if I measure the voltage difference from here to here, it's some amount, right? So let's say 1 volt. So I have 1 volt from here to here. Then I have 1 volt from here to here. I have 1 volt from here to here. I have 1 volt from here to here. It's all the same voltage difference. Therefore, the electron density, the amount of charge that we have for each of these little capacitors is the same, right? If you break this capacitor into smaller units, we see that for each of them, we have the same voltage difference, and therefore the same positive charge here and here, positive, negative, positive, negative, positive, negative. That seems obvious, but we need this to go to the next step. Okay, so that was case number 1. Let's go to case number 2 and consider a slightly more interesting situation. So again, the device is on, so VGS is greater than VTH. The source is still at 0, but we apply a voltage to the drain. So VD is greater than 0. So here's the situation. Again, we draw the device quickly, like so. We have our source and drain, and source is at 0. The gate goes to a battery, VG. The drain also goes to a battery, VD. Okay? Now, the device is on. because the gate voltage is higher than the threshold. So we must have electrons here, free electrons. All right, so free electrons have accumulated in this area. So let's draw some free electrons. There's some free electrons here. But now, do we have a current? Yes, we do have a current because we have a channel capable of conducting current, like a resistor, and then we have a voltage difference from here to here. Let's say this is 0.5 volts, this is 0, so from here to here, we have 0.5 volts if you look at this as a resistor, so that resistor will carry some current. So there's a current. Okay, so in this case, there's a current. I will draw an arrow this way to comply with the convention, meaning positive current. So positive current is flowing this way. We call that ID, the drain current. Okay, so far so good, and that's relatively obvious. But now let's think about this a little more carefully. We have a current flowing through a resistive path. Okay, this is a resistive path. It's a long resistive path, and a current is flowing through it. So you can think of this as a many little resistors in series, right? So then, is the voltage here, or maybe I start from here. So the voltage here is 0 because we've connected to 0. How about the voltage here? If I go and put a voltmeter at this point of the channel and measure this voltage with respect to 0, is it the same? No, it's not the same because we have a current flowing through the resistance. So it gives us a voltage drop. So this voltage is a little larger than 0. This voltage is a little higher than this. This voltage is a little higher than this. And ultimately, this voltage has to be equal to, for example, 0.5 volts. So because we have 0.5 volts on this side and 0 on this side, and we have a resistive path, the voltage varies from 0.5 to 0 with respect to 0 if I travel from here to here. Okay, that's the key point that you have to remember. So that's a weird capacitor. Ordinary capacitors wouldn't be like this. You had one plate here, that's it. But now, we have a plate here, but in this plate, what have we done? We are allowing a current to flow through a resistive path. And that creates a voltage drop this way, in addition to whatever we applied between the two plates. Okay, so the key point here is that the voltage around here is close to 0, but as we travel towards the drain, the voltage increases and eventually is equal to the drain voltage, 0.5 volts, for example. All right, so we say voltage along the channel increases as we go from source to drain. Okay? All right, so far so good. Now, let's go back to this notion of electron density. We would like to see now what happens to electron density at different points. So if I go and sit over here, take a little length here, and measure how many electrons I have per unit length or unit width or something, how many electrons do I get? Well, okay, well we know that the amount of charge that we would have here on a capacitor should be in proportional to the voltage, in proportion to the voltage that we have between this plate and this plate. So how much voltage difference do we have here? Well, this is 0, and that's the gate voltage, right? So if the gate voltage is 1 volt, we have 1 volt from here to here. Because we have 1 volt, we have a certain density of electrons at this point. But now, how about here? Well, the gate is still at 1 volt with respect to 0, but the channel voltage is not 0. The channel voltage, as we just said, rises as we go this way. So if I measure this voltage with respect to ground, it's not 0, it's 0.3 volts maybe. So if this is 0.3 with respect to 0, and this is 1 with respect to 0, the difference between these two is 0.7 volts. So the voltage difference from here to here is less than the voltage difference from here to here. If the voltage difference from here to here is less, the charge density on these two plates, on this plate, will be less because V is less, Q is less. So what's interesting is that the electron density of the channel varies from this side to this side because the voltage across the local capacitor varies. The voltage across the local capacitor is minimum here and maximum here, right? Because the source is at 0, the gate is at certain voltage, so we have this much voltage difference. Whereas the drain voltage is not 0, the drain voltage is some positive value, which means this difference is less. So let me give some values here so that we can play with them, 1 volt and 0.5 volts. So we see that the voltage difference here between these two. So delta V is 0.5 volts. Okay, so let me play with numbers so that it's nice and... So let's make this 0.6 volts. So this is 0.4 volts so that we can clearly see what's going on. 1 volt minus 0.6, 0.4 volts. On the other hand, here, delta V is equal to 1 volt. So that means that the charge density is less here than here. So very roughly speaking, this is what we should see. Again, just qualitatively, we say Q of channel, the electron density inside the channel, is as a function of X. Okay? In fact, let me try to align this with the device itself to make it nice and clear. So I start X right here at the beginning of the channel. So here we have maximum voltage difference. So we have maximum charge density, Q of channel. And then as we travel this way, because the voltage difference across the capacitor has reduced, the charge density has reduced. And keeps going down and down, right? And this is the end of the channel here. So it gets to some value. Is it 0? We don't know how much it is. We don't know. How does it vary? We don't know. All we know is just it goes down. So that is the important point that we see when the drain voltage is not equal to the source voltage. Okay, so we see that the channel charge goes down. Okay, so we need to remember these later on when we want to derive the IV characteristics. Okay, so let me make one more point about the dimensions of a MOSFET before we go to IV characteristics. All right, so I will draw this again quickly. Here's our device. And source and drain. Okay, and that's our oxide. Okay, so there are some dimensions in this device that are of interest to us. So I will write those down. First, this is the direction of current flow from source to drain or drain to source. This is called the length of the device. So we call this dimension from here to here length. This dimension into the page is called the width of the device. So that dimension is called the width of the device. So remember that these are highly doped regions in plus. And of course we have a substrate under all of this. So that's our P substrate. Now, of course there was a third dimension, if you remember, which we call the oxide thickness, this one. But it's important to understand that if I am a circuit designer and I'm playing with these devices, I can adjust some of these dimensions, but not the others. The dimensions that are under my control are L and W, because when I draw this device in the layout, I can make W big or small, I can make L big or small, within some limits, of course. But the oxide thickness is not under my control, because when the chip is fabricated, it is fabricated with a certain thickness of oxide, and that's the value that is given to me. So those I cannot change. All right, so the circuit designer can choose W and L. And we will see that, in fact, W over L plays a critical role in almost everything we do from now on. All right. A quick note about this L. So when I draw this source and drain, these source and drain areas, sometimes you might have seen that this doesn't start at the edge. It actually starts from here. And you might have been wondering why that is the case. Well, this is because during fabrication, when we implant these regions here during semiconductor processing, and then heat this up, heat the chip up for all of these to settle, etc., to heal, as they call them, to anneal, as they call them. What happens is that this actually, during that thermal processing, partially penetrates this way. We say it diffuses that way. So it's inevitable to have a little bit of overlap between the source area and the gate area and the oxide area. This protrusion this way happens during fabrication. And of course, similarly on this side. So now, when we say L, which L are we referring to? When I draw the layout of the circuit, I actually draw this structure from here to here. When the chip is fabricated and device is built, this area actually protrudes under this, and that's not under my control. So we distinguish between these two L's. We say this is the drawn L, so you might call this a drawn L. This is what we draw in the layout that we send to fabrication services. And we will call this L effective because this is the actual L that device will have, which is less than L drawn by some amount. So in the calculations that we perform from now on in this course, we are only concerned with L effective, not L drawn. These two differ by some amount, but this is what will appear in our equations. So just remember that. Okay. All right, so let's go ahead and try to derive the IV characteristics of the device. So we will spend some time on this, derivation of IV characteristics. And again, we have to understand the physics of the device. We start with fundamentals, basic stuff we know about semiconductors and general physics, and try to find the relationship between the current that flows through the device and the voltages that we apply around the device. Okay, so to do that, I will need to first talk a little about the channel charge density following the behavior that I've studied here. So let's start with some study of channel charge density. We qualitatively studied it here. We said that, well, if there's a drain voltage applied, then the channel charge density is not constant. It's maximum over here and minimum over here, because the voltage across the capacitor decreases as we go from the source towards the drain. Okay, can we write an equation for the charge density inside the device, for the charge inside the capacitor? Okay, well, we start from here, Q equals CV. We know that's true. So what we will try to do is the following. First, so case 1, we say VG is greater than 1 threshold and VD equals 0. So remember this case here? Very simple. The charge density is uniform, same thing, same value all over the place. Okay, I would like to write an equation for the charge in the channel. So here's what I will do. I'll say Q of the channel, meaning the electrons that we have in the channel, is equal to C. C, how much is C? Okay, C is the capacitance of the structure here, right? The capacitance between this plate, the gate plate, and all of this here. So how much is the capacitance? Well, often in our analyses, we write it like this. We say the area of the device, W times L. L from now on indicates effective L, so just remember that. Area of the device times some quantity, which is easy to find, and that's called Cox. Cox is the capacitance of the structure per unit area, per meter squared, per micron squared, whatever you like. So Cox itself is capacitance per unit area. The unit would be, for example, farad per meter squared, or more justifiably or more interestingly would be femtofarad per square micron or something. Okay, so the area of the device times the capacitance per unit area gives us the total capacitance. So that's this term here. Now we need voltage. So can I just write VG, the voltage that's applied to the gate, this guy here? Well, okay, so if I write it like that, this equation says if VG is 0, you have no channel charge, which is true. But if VG is 0.1 volt, do we have channel charge or not? If VG is 0.1 volt, well, VG has to be greater than a threshold to have channel charge. If VG is less than a threshold, we have only depletion region charge, meaning ions, right? And the threshold is not really 0.1 volt. The threshold is 0.2, 0.3, 0.4 volts. So if VG is less than a threshold, let's say 0.1 volt, the channel charge is still 0. So this equation doesn't exactly do what I want. So how do I take care of that? In other words, the channel charge begins when the gate voltage exceeds a threshold. So we need an offset of a threshold inside here, meaning we just offset this by one threshold. So now you can see that if VG is equal to one threshold, the charge is 0. We have no charge up to one threshold, and then we have charge, we have channel charge. So the channel charge is proportional to this quantity, not just to VG. In fact, usually we write this as VGS, the gate source voltage difference. Okay? And this has a name. This is called the overdrive voltage. Overdrive voltage, or more specifically, we call it the gate source overdrive voltage. And by overdrive, we mean whatever we have above and beyond one threshold. If we had only VGS equals VTH, we still had no channel, very little channel, right? So it's beyond the VTH that we would have a channel. That's why this is called an overdrive, the overdrive voltage. Okay, so we have found the total charge in the channel for a given gate voltage if the drain is at 0. We're happy with that, right? Okay, so this is not really density yet because this is the entire charge in the system, right? The entire charge they would measure from here to here into the page. All of that together is this much. But that's okay for now. Okay, so, all right, now can I make this a local quantity so that it becomes some sort of density? Because I am really interested in seeing how the channel charge is, how much it is here, how much it is here, how much it is here, etc., right? So if I take a little length, an infinitesimal length, a dx if you will, how much charge do I have there, right? So what we will do is we'll divide this by L, because L is from here to here. We'll divide by L to give us per unit length. And that's what we will call the density of the charge, per unit length, because I'm interested to see how much charge I have in each of these little pieces. So density Q charge. So let me write this total so that we know it's total, it's not density. And this will be density, and we won't really bother to call it density. Well, maybe I'll just say dense for now. So that's just W times Cox times VGS minus VTH. So in other words, if this had a unit of Coulomb, so Coulomb, right? This would be unit of Coulomb per meter. Coulomb per meter. Because we divided by the length of the device. It just tells me how much charge I have per unit length. The unit length could be 1 micron, could be 1 angstrom, could be 1 nanometer, whatever you like. Okay, so far so good. Now let's go to the more interesting case where the drain voltage is not 0. So we'll go to case number 2, and we say the gate voltage is still, so VGS really greater than 1 VTH. And so this should also be really VGS, because we have to know something about the source, right? If the source and the gate have the same potential, we don't have a channel. And then VD is greater than 0. So we are back to this case here. Okay, so now the situation is a little more complicated, because we see that the channel charge is some value here, and it keeps going down. Okay, so do I have a value right here? Yes, because at this point, the gate source voltage is equal to what we applied. We have the entire gate voltage appearing between the gate and the source. So right here at x equals 0, we still have this equation. W Cox VGS minus VTH. But now if I go somewhere in the middle, at some arbitrary value of x, then what happens? Well, over here, the voltage that we have in the channel with respect to 0 is some amount. So let's call that right here V of x. So if you take a voltmeter and place one terminal at 0 and one terminal into the channel right here, you will measure V of x. It's a positive value. It starts from 0 and goes towards 0.5, 0.6 volts, right? Okay. So that's the voltage that we measure here. Now, what does that mean in terms of this capacitor voltage? Right at this point, at this x value, we have a certain gate voltage. But this plate voltage is no longer 0. It has risen by V of x. So the charge density at this point is less than the previous case, because this voltage has risen as a result of this current. So in this case, what we would have is Q channel, if you want density, is equal to W Cox, and then what we have here is VGS minus VTH like before, but then we have to subtract from this the local voltage at that point, V of x. Right? Because the net voltage appearing across this capacitor is the gate voltage minus V of x, and of course we have to subtract the threshold to account for only electrons in the channel. All right, so this is the density of charge inside the channel. Okay, very good. All right, so now we have this equation in terms of the gate voltage that is applied, this V of x that varies, of course, from here to here. We don't know how it varies. We have no idea. We just know that it increases from here to here. And our objective is still to determine the drain current as a function of VGS and VDS. Okay, so this was number one, channel charge density for the general case that we have some gate voltage and some drain voltage. Now our second task will be to write the current. So let's go and do that. You just have to remember this equation here. Okay, let's add a page. Okay, so our second task is drain current. Okay, so let's rewind to when we learned about physics of semiconductors. We said that in a general semiconductor with some doping, when we apply an electric field, we obtain a current. And we know that when you apply an electric field, the carriers reach a certain velocity, right? And if you remember, we said that the velocity of carriers is equal to the mobility times the electric field. Mobility indicates how mobile the charge carriers are. So we saw that, for example, mobility is higher for electrons than for holes. And the velocity that we obtain is like this. As I mentioned before, this is like a terminal velocity when a parachuter falls with the parachute open. So the electrons eventually reach this velocity, and that's, at this velocity they flow through the semiconductor. Okay, so we should be able to calculate the velocity of carriers, or at least we have this equation for them. That's good. We also know something about E, the electric field. We know that the electric field is equal to minus dV over dx. The electric field is the derivative of voltage with respect to distance with a negative sign. All right, that's what we learned from physics. Okay, so that means that the velocity is equal to mobility with a negative sign times dV over dx. So if I go anywhere in a semiconductor, and at that point, at some point in the semiconductor, I measure certain velocity for the carriers, and I measure the derivative of voltage with respect to distance at that point, they have to be related by this equation. All right, so remember that. So we'll just put this in a little box on the side, and we'll come back to it in a second. Okay, so my objective is to find the drain current. And I have found the following. On the previous page, I found the charge density in the channel. Charge for 1 micron of length or 1 meter of length. Here, I have found the velocity of the carriers in terms of some internal voltage, some voltage anywhere we have V, dV over dx times mu times minus 1 is V. Now the question is, can I relate all of these together? So what we have are V, we also have Q of the channel, right? And what we are looking for is the drain current. Okay, so that's what we want to do. All right, well, it's not that bad. So here's how it goes. Let's draw the device again very quickly. We have source and drain. And of course, we have the right voltages applied everywhere. Some voltage at the gate, source at 0. Some voltage at the drain. And we are interested in what's going on in this channel. A bunch of electrons flowing from left to right. Okay, so let me erase these unwanted lines here and change the color to this color. Okay, well, if the charge is moving at the velocity of v in the channel, right, it's moving, the electrons are moving at the velocity of v this way, and I go and pick a length equal to v meters, then what can I say? This is something similar to what we discussed a long time ago when we were studying current transports, diffusion, and drift for semiconductors in the first few lectures. So if I have some mobile charge and I take a snapshot of the mobile charge, the charge is moving, but I take a snapshot at one moment and I see that I have a certain amount of charge from here to here in v meters. How much is that charge? Well, that's easy because I take the charge density, multiplied by the length, that gives me the total charge in that length. So the total charge in this length, total charge in this length is equal to the length, which is v meters, times the density, the amount of charge per unit length. So we multiply v, which is the length, v meters, times the density of charge. Do you remember the equation for that? So QCH dense. So that's v times, this was w. We dropped L because we found density, times VGS. Sorry, there was a Cox here. Let me put the Cox back in here. Okay, WCox. Then we had the VGS minus VTH. And unfortunately, we had also minus Vx because the potential at somewhere in the channel, along the channel right around here, was not equal to 0. It was V of x. So we had to subtract that from the effective voltage across the capacitor. Okay, so this is the total charge that I find in this length of the device. If the device has current going through it, and I take a picture. Now, what's the big deal about this? Well, okay, so this is the total charge enclosed in this, right? Of course, running to the page 2. This is a little bar of charge that's moving this way. So if I look at this charge in this bar, and it's moving this way, and I wait 1 second, what happens? Well, the charge moves v meters in 1 second. So all of this charge moves from here to here in 1 second. In other words, if I sit at this interface and I measure the total charge that passes this interface from left to right in 1 second, how much do I measure? I measure this. The total charge passing through this interface in 1 second is this. And that is the definition of current. Current is the total charge that passes through an interface in 1 second. So this is actually the current. Okay? With a little proviso, we need a negative sign here and a negative sign here. Why? Because we are looking at the electrons. Electrons are going this way, so positive charge would be going that way, so a negative sign here. All right, so far so good? Okay, so that is the current. So let's write out everything we have. We know what the equation we have for V. So we write ID is equal to minus, so V is given by minus mu dV over dx. So that's just plus, and mu is mu n because we are dealing with electrons. dV over dx, and then all of this stuff. WCox times VGS minus VTH minus V of x. And again, remember, V of x is the internal channel voltage at some point. So this might be right here. At this point, it would be V of x. And I hope you're not confusing capital V, which means voltage, with lower v, lowercase v, which means velocity. All right, so this is the equation for the drain current that flows through this device when we have a certain gate source voltage. But in terms of this V, which is very strange, this V is some x-dependent V, right? It's something here, something here, something here, something here. This is a variable value, right? V itself, and maybe its derivative too. All right, so our objective is to find ID in terms of VGS and other known quantities, things that we have applied from outside, not in terms of V of x. Right? We don't know what that voltage is, and it's variable anyway. But fortunately, there's a way to calculate the current and eliminate this V from the equations. So let's go ahead and do that. Okay, so here's what we'll do. It's a differential equation, right? Very simple. So we'll multiply both sides by dx and integrate both sides. So we have integral of ID dx is equal to mu is, let's assume, is constant. WCox, they all come out of the integral. Mu n WCox, integral of. We have this dV. So VGS minus VTH minus V of x dV. Now we just have to pay attention to the limits of the integrals. Okay, x goes from where to where? Well, x starts from here and goes to here. So at this point we have 0, and at this point we have L, effective L, which we always denote by L in this course. So this goes from 0 to L. No problem there. This side we have to look at the voltage, this internal voltage. How much does it go from to? Well, at this point, how much is the voltage on the channel? It's 0 because we're right next to the source. So it's 0. And at this point, how much is the voltage in the channel? Is equal to the drain voltage because the drain is connected to it. So that's what we call VDS. So now it's easy to integrate. Let's see what we get. You see that, interestingly, V drops out because after integration, we have the substitution of 0 and VDS. So V of x goes away. All right, ID is constant. It doesn't depend on L. Is that true? Yes, because current cannot disappear. Electrons start from here, and they travel. They have nowhere else to go, so they have to end up in the drain. So the drain current is always the same value, whether you measure it here, or here, or here. So we can take it out of the integral. This gives us L ID equals mu n C ox W. I keep moving things around. We'll see later why. And then we integrate this. So we have VGS minus VTH. Because this is a linear term, we get V, and then minus 1/2 of V squared. And this has to be evaluated from 0 to VDS. V is the variable, and it has to go from 0 to VDS. So we divide by L, and we obtain ID is equal to mu n C ox W over L. And then we have VGS minus VTH. V it has been replaced by VDS. For 0, we just get 0, so no worry about that. Minus 1/2 of VDS squared. So this simple, beautiful equation relates the current that flows through the MOS device as a function of the voltages around it, the drain source voltage and the gate source voltage. How about the body, the substrate voltage? Well, we don't worry about that. We assume for now it's the same as source voltage, so it's not in the picture at all. Okay, so we will spend a lot of time understanding this equation and trying to see the significance of each term in there, each coefficient in there. Does it make sense that we have all these coefficients? All right, so first of all, let's try to quickly plot this and see what it looks like, and then we'll try to analyze it. All right, so let me change the color of my pen again to maybe red, and let's try to plot this. Okay, so I actually plotted here because I need more space. So here's ID. Okay, so now we face a dilemma. ID is a function of VGS and VDS. So what do I plot ID against? Well, in cases like this, we have to keep one parameter constant and vary the other parameter. So, for example, we can keep VGS constant and vary VDS, or keep VDS constant and vary VGS. So we have two sets of plots, ID versus VDS and ID versus VGS. We can't mix these two, at least not arbitrarily. Okay, so let's assume that VGS is constant. All right, so we say VGS is constant. And from a circuit point of view, this is the experiment that we are conducting. We have a MOS device. Its VGS is constant. And we are varying its VDS. So we are applying a variable voltage between the drain and source. And we're plotting the resulting current, ID. Okay, and this equation tells us what we get. So what type of behavior is this? Well, it's a parabola, right? It's a parabola. It starts from 0 at VDS equals 0. And then as VDS goes up, first it goes up sort of linearly. If this term is very small, you see that ID as a function of VDS is a straight line. But then eventually it sees the effect of this second order term, and it reaches a maximum. The parabola reaches a maximum in this case. Because this coefficient is negative, this coefficient is positive. So it goes up and reaches a maximum. Okay, of course, after this, some other things may happen. We'll get there, but that's part of the parabola. Okay, so at what VDS do we have the maximum? That's not hard. Take the derivative quickly, and you will see that at this point, VDS should be equal to VGS minus VTH. Amazingly, is the overdrive voltage that we talked about before. So when VDS is equal to VGS minus VTH, the drain current has reached its maximum. And can I find this maximum? How much is this anyway? Yes, that's not that hard. So we go in here and we say for VDS equals VGS minus VTH, we have reached the maximum. So we replace VDS with VGS minus VTH, subtract, right? That's very easy. So that gives us this value here is equal to 1/2 of mu n Cox W over L VGS minus VTH squared. You can see that this is VGS minus VTH, so this gives us the squared. But then we also 1/2 of VGS minus VTH squared, so this 1/2 gives us a 1/2 here. And that's what we got there. Very interesting, right? It's a unique characteristic. Diodes have an exponential characteristic. If you know about bipolar transistors, they have an exponential characteristic. But this is not exponential. This has this type of behavior. Okay. All right. So one other question about this before we continue. So let me ask you a following question by changing the color to blue. All right, so let's suppose that we had some VGS, maybe 1 volt, right? And we got this characteristic. Now, what if we pick another VGS? Let's say VGS is 0.8 volts, a little less. Then how does this plot change? Okay, well, we just follow and see what happens. If VGS is less, two things happen. This point goes to the left, and this point, this height, also decreases. So the new plot for lesser VGS should be like this. It reaches a peak around here, and the peak is also lower than this, right? The maximum is lower than that. So it will be another parabola that reaches a maximum here. So this is for a lower VGS. How about a higher VGS? Well, same thing. If you have a higher VGS, the maximum occurs here, and it will be at a higher point. So we get another one way up here. Okay, so that's interesting. In other words, these maxima are not aligned, right? This maximum happens here, the next maximum happens here, the next maximum happens here, and so on. Okay. Now let's go back to all these parameters that we have here and try to see why they are here. Do they make sense? We say that the current that flows through the device is proportional to the mobility of charge carriers. Is that correct? Yes, that makes sense, because the higher the mobility of the charge carriers, the higher the velocity. The higher the velocity, the higher the current for a given electric field, and therefore the higher the current, the higher the current that we get. So that's obvious. Cox. The larger the Cox, the larger the current. Why is that? Well, if you remember last lecture, we said that if we bring these two plates of the capacitor closer to each other, meaning Cox goes up, then because the capacitance has gone up, for a given voltage, we have more charge density on both sides. So for a given voltage, Because the capacitance is higher, we have more charge, we have more electron density. We have more electron density. In a sense, we have less resistance, and in a sense, we have more current. So that also makes sense. All right, it's proportional to W. Well, this is like a resistor. You know that if you take a resistor and make it wider and wider, we have more room for current to flow. It's just like a big hallway. If you make the hallway wider and wider, more people can go through it. So as the device becomes wider, it is capable of carrying a larger current. So that also makes sense. And it's inversely proportional to L, because if the device is longer, it's like a resistor that's longer. A resistor that's longer has a higher resistance, so similar ideas apply here as well. And then we have VGS minus VTH, which again makes sense because that's the overdrive necessary to create a channel of electrons, and that's why it's here. Okay, so that's a simple equation that tells us how ID depends on VDS in this regime, right? As we go from VDS equals 0 to some maximum value. Now, something peculiar that happens in the structure, and I mentioned briefly before, is right around here. Right around here, there's no current, right? ID is 0. But is the device off? No, it's not off, because the gate voltage is still there. The gate voltage is some amount. So around here, VDS is 0. This voltage is 0. We have no current going this way, but there is a channel inside the device. So as I said, this is a unique property of MOS devices. They can be on, they can have a channel of electrons, but they have no current. So ID is 0, but the device is on. Okay. Let's try to plot something else as well, if we are curious. And that's ID as a function of VGS. Because we said we have two voltages, so we have to keep one constant and plot as a function of the other. So in this case, we keep this constant and vary this. So let's go back to the equation. Let's see what happens. So VDS is constant, it's just some value, but VGS is changing. So then what happens? All right. Well, remember from last lecture, what we discovered was that if VGS is less than a threshold, we have no ID. Right? Because there's no channel. And then it begins to take off. So is that reflected properly in this equation? If VGS is less than VTH, is ID 0? No. So it means that this equation is valid only if VGS is greater than one threshold, right? Otherwise, this equation is not valid. It doesn't predict things correctly. So we have to resort to our own knowledge of the device for less than a threshold. We should not rely on this equation. So, well, when the VGS is less than a threshold, there's no current, the device is off. Okay? All right. So then when VGS starts increasing, ID starts going up, as predicted by this equation, right? Now, this equation says ID is proportional to VGS. So VGS minus VTH. So it means that it goes up straight. But that's actually not true, and we will have to see later why that's not true. So I'll just put a question mark here for you. Qualitatively, we know this should happen. No current, and the current goes up. But how it goes up, we'll have to come back to it a little later. Okay, so we studied the basic characteristics of the MOS device, and we discovered that the ID and VDS are related by this very simple equation. It's a parabolic behavior. Well, some other interesting questions that come up are, for example, I plotted this up to here deliberately What happens after this point? For VDS greater than this value, do we go down, just follow the parabola, or do we do something else, right, for these things? So that's something that we have to study. And then around here, we can also see some interesting behavior. We can see that if this term is very small, when you start with very small VDS, the squared term might be small, right? If that term is small, we see that ID and VDS are related by a simple constant value, right? So ID and VDS are linearly related. There's no second order term. We don't have a parabola. So around here we can approximate the parabola by a straight line. And that has some very interesting ramifications. So I will keep you in suspense until next lecture. We will talk about all of these interesting concepts. I will see you next time.